Right, so this week we're going to be doing a Pycom tech counter about over-the-air firmware updates. We'll be explaining how to perform a firmware update, and we'll give you an example of some software we've written to do that. So we'll be going over firmware versus code in the context of Pycom modules and what do we mean by firmware specifically. We'll go over how you can update firmware on a device over the air without actually connecting to the device via cable, and how to also update your code, your Python files over the air. We'll then have an example of an over-the-air update being triggered by LoRa, so we'll go through explaining how to connect, how to set up the Things network, and how to then send downlink messages to your device from the Things network. So today we'll be overviewing this procedure. We'll have a node, which will be just a regular low-pi connected to an expansion board with a LoRa antenna, nothing fancy happening here. The node will be sending regular data over LoRa. It could be temperature data or anything. For this use case, it's just sending out dummy data. And then we'll come along and we'll request that the device does an over-the-air update via a downlink message. This gets sent via LoRaWAN to the node when it sends its next packet of data to the network. When it receives this special command to trigger an over-the-air update, the device will then connect to a Wi-Fi network, and it will begin the update procedure. So, what does firmware look like on Pycom devices? We have the actual firmware on the device, which contains all your networking libraries, your MicroPython interpreter, that sort of stuff. As well as this, you can have what's called frozen modules. These are modules, just regular Python files that you can freeze into the firmware. This prevents people from tampering with them and so on. They're compiled directly into the binary. So we offer a method of updating the firmware over the air. This is what you do when you use the Pycom updater tool that does it via UART, but we also have some functions that let you do this over the air. The devices also have a flash file system. It's just a regular FAT file system that's on the onboard flash of the device. And there you'll often see your main PY and your boot PY files. You can also have directories such as lib, which you chuck your library files in. You can also include CSV files or WAV files, things like that, anything that you really want. It's just a regular file system. So we'll be going over the different procedures between updating a firmware as well as updating files that are present on the flash file system. So today we'll have two bits of software. There will be an update server, like we showed in the diagram earlier. This is just a HTTP server written in Python 3, and it will serve a manifest file to the device, which is just a list of what it needs to perform to be up to date, and then the device will then download the appropriate files via regular HTTP. On the device side, we have a OTA library that's split into two layers. There is the core OTA sort of procedure. This handles getting the manifest file, parsing it, understanding what the different entries mean, and so on. And then on top of that, we have another layer, which is the Wi-Fi OTA layer. This is specific to that transport mechanism. So for Wi-Fi, it will start a Wi-Fi connection and connect to a HTTP server. You could easily replace this layer with something like Bluetooth or LTE, whatever you want to do in your particular scenario. In this example, we'll be using Wi-Fi because it's the simplest. So I'll give you a quick tour of the code. If you want to play along at home, you can find the code if you just go to the Pycom GitHub page, which is github.com/Pycom. We then have a Pycom libraries repository. And then in there you'll have examples and then OTA. So this will include all the software that I'll be using today and all the instructions on how to use it. So you can join along if you want by downloading this. So I've already got it here on my desktop. Inside this folder you will have OTA server.py. That is the server-side code. So we'll have a quick look at that. So this software expects to see directories structured like this. It has the top level directory should be numbered by the version numbers. So this is version 1.00 and then 1.001. So this is the slightly higher version. And then inside these folders, you should have the normal sort of file system structure that you would expect on your device. So you can either have flash or SD, because if you've got an SD card connected, you can also update files on that. And then here we have our normal code. So there'll be your main PY, and then the OTA library is present here. So with each update, you'll need to include the OTA file, otherwise it will you'll stop being able to do the OTA if you do an update that doesn't include that. You can also include firmware binary files. They just live in the top level directory. And they also just have a version number. I don't have any in this example, but the documentation at the top of the script will explain how that works. So it's just firmware underscore with a version number .bin. And that is just a appimage.bin file that's generated by our build scripts. So when you start up the server, it starts up a standard HTTP server on port 8000. And if I open a terminal, we can start it up and I'll show you what it produces. I'll need to use Python 3 for this. So that should have started the server. So if I now go over to my web browser, and then I'll just go localhost port 8000, and then we load up manifest.json. So this is a file that the server automatically generates, and it contains a list of files that will be deleted, files that are new to this version, files that you need to update, and what version this manifest reflects. So you can pass it a version number. So let's say we're on version 00. It will tell you what files you need to update or delete or download to make your node go from this version to the version provided in the manifest. So if you don't provide a version, it just shows you everything that's available. So in this example, we don't have firmware, for example. So this is just a standard HTTP server, so it will serve these files. You can see it provides URLs on where to get the files. It provides where they should go on the device, and also a SHA-1 hash, so that once you've downloaded it, you can verify that the the updated file is correct, so that you're not flashing corrupted data to your device and then bricking it. So this is literally just a simple HTTP server written in Python, and for most files it will just serve them as they are, with the exception of manifest.json, which it will go through and look for which files are different, which have changed, and so on. It will scan this directory for the highest version number it will find based on the Python loose version library, which we import here, and then whichever it determines is the highest version number, it will then generate a diff from the version that you provided it to that latest version. You can have a look at the code yourself if you wish to understand what's going on here in a little bit more depth, but there's nothing too exciting really. So on the device side, we then have the OTA library. So this is split into two layers like we talked about before. There is the base class, OTA, which has two functions that are not defined. Those need to be implemented in a subclass for the specific transport mechanism you're using. In this case, it will be Wi-Fi. And then underneath that, you'll see all the code for actually doing the update. So the main procedure happens here in update. What happens is we get the manifest from the server, which will use the transport specific get data. So in Wi-Fi, if we scroll down here and have a look at Wi-Fi, get data just opens a HTTP socket, connects, and then receives whatever data that has, and then performs hashes and different things. We'll come back to this in a second. So on the update, we'll get the manifest. If the manifest we get back is just null, then that means we're already on the current version, so we don't need to do anything. Otherwise, we'll need to go through all the new and update files and download them. If you wanted to, you could be a bit smarter, and for files that aren't new but only require an update, you could implement a sort of a diff to minimize even further the amount of data that you need to send. But here, just to keep it simple, if there's a difference in a file, then we just simply download it again. We'll have 5 attempts, and yeah, it just tries to download the file. Then we also back up files, so it's important to not just override the files straight away. You should download all the files first with a different name. So the get file function actually downloads them and appends .new to the end of them. And only once you've got all the files and you've verified all of the hashes, should you then start moving your existing code. Otherwise, should the update fail somewhere later down the line, you may find that the device is in a sort of a halfway state where it might not function properly. So for any files that we need to update, we then back them up. For new files, there's nothing to back up because they're new. So if it's a file that did exist, we back that up by literally just renaming it with .back on the end. And then the new files, now that we've backed all the old files up, we can rename the files with .new back to their correct name. This code doesn't actually implement a mechanism to roll this back, but that should be quite trivial to implement should someone want to do that. Files that need to be deleted, again, you can't just delete them, you need to actually keep a backup of them. So what we do here is in delete file, it will actually just rename them to back_del, or appends that to the end of the file name. And if it finds a file that already has that name, then it will delete it because that means it's 2 versions old, so we no longer require a backup of that. Yeah, so that's that. And then, so for firmware, we need to do something slightly differently. This so far has all been relating to files on the flash system of the device. And to write to the flash system, it's just like you would in Python be writing a text file or whatever. You just need to do, let's find the code here. Do a quick search. Yeah, there we go. You can see with open and then the path that you want to be writing to. It's just a regular file. But if you're writing to the actual firmware of the device, you have to use the OTA functions that we provide. So if we quickly go over to the Python documentation and scroll down to the API docs and have a look in Pycom, you'll find that there is a OTA start, OTA write, and an OTA finish function. What these allow you to do is to overwrite the firmware on the device, and the device features a sort of 2 versions of firmware. You have the one that you're currently running and a blank one. So when you do OTA start, it tells the device that we can start writing to the slot that's not currently being used. Then OTA write buffer, write will send whatever you pass it in the buffer, it will pass that into the second slot for firmware. And then once you can do this in as many chunks as you want. We recommend using fairly small chunks just to keep it regular. And then when you're done, you just call finish, and what that will do is that will then verify the hash of the firmware just to make sure it's all been written correctly. Our build script appends an MD5 hash to the end of every firmware image. The app image.bin file has that appended at the end, so it will verify that it's correct, and if it is, it will then switch the slot from the one that it's currently running to the next one, and then the next time you reboot the device, the new firmware will be running. So for the actual firmware, that's what we do here. And you can see that here with, so this calls get data, but firmware equals true, and then if we have a look in that code, you can see it here, OTA stop, OTA write, and OTA start. So that is basically everything that's happening there. I will now demonstrate how to get this running on a device. First things first, we'll need to, actually I'll show you the example we have here. So we're just importing the Wi-Fi OTA, we're setting it up. You need to give it your SSID, password, and the IP address of the server, and then the port number. We're turning off the Wi-Fi first, and we're connecting to LoRaWAN. We'll fill these details in a second. We'll go over to the Things network and we'll get the app EUI and key. You then join the LoRa network, and then this device will just, this example will just send 456 to the LoRa network every 5 seconds. But if it receives a downlink message containing 1, 2, and 3, it will begin to perform the OTA procedure. So it will then connect to the Wi-Fi and then begin the update procedure. So under normal conditions, this device will just be connected to the LoRa network, and it will be pinging out data every 5 seconds, and then should it receive back a special command, it'll then go into OTA mode. So we'll go over to the Things network and we'll start setting this up. First I'll open some notes. So I've already logged into the Things network. I will then go over here and click on account. Oh, no, console, sorry. So it's console.thethingsnetwork.org. We'll click on applications and we'll create a new one. We'll give it a unique name and we'll call it Tech Counter OTA example. So we'll need to note this down, the application ID. I'm just going to save it here for later. We'll give it a quick description. This is an example of OTA updates via LoRaWAN. And then when we click add, the EUI, the application EUI and everything will be created. So we need to note that down. We'll copy that. We'll note that down for later. We'll need to know the handler. So I should have picked a region. When setting up the application, you have to pick a region. It defaulted to Europe, which is correct for me, but that might not be the case for you. So make sure you select the correct region. So for me, we'll be using the EU handler. And then you'll also need the access key. So normally this should be kept private, but for this video, we're just creating a quick dummy application that will be deleted after the video, so we don't have to worry too much. Next things next, we need to register the device. So we'll need to give it a unique name for our application. So in this case, since we don't have any, it doesn't actually matter. We'll just call it LoPy OTA1. We now need to get the device's EUI. So if you've downloaded the code that that was provided on GitHub, there will be a getID.py file. So this is a quick little script that will return the EUI of the device. So if you just get PyMaker open in Atom, you can then connect. and then open this file, and if you just press run, it will print out a number. So that's the number we need. Unfortunately, you can't copy and paste from this window, so I'm going to have to type it over manually. So 70B3D. Let me just double check that. Yep. So we'll copy that over and we'll paste that in here. It's accepted it was the correct length, so that's good. And then we'll click register. And this will give us a application EUI. We can copy that over. We'll need to note that for later. Sorry, that was supposed to go here. You'll also need to note down the unique name you gave the device. So I used LoPy OTA1. So we'll note that down, and then the application key. So we'll copy that down. Again, this is something that you should normally keep private, but for the sake of this demo, it doesn't matter too much. So there we go. Now this LoPy is now configured to work with the Things network. What we'll do is we'll open up main.py, and then here we have to enter the app EUI and the app key. So I'll go back to my notes. The application EUI is that one. That can go there, and then the app key is there, and we will enter that there. So we'll save, and then we can click upload, and that should upload all this code to the device. It takes a few seconds. Okay, the device is rebooted, and now it's trying to join. It usually takes a few seconds. There we go, the device is joined. So if we now go back over to the device in the Things network, we can click data, and we should start seeing it soon. Oh, didn't connect. Why is that? Bear with me just 2 seconds. I have to verify that I got the EUI down correctly. We'll just run this quickly again. Unfortunately, you can't copy and paste from this pane down here, which makes it quite difficult to get some of these numbers back. Seems to have connected. It might be because it's already registered in my other application. Give me 2 seconds. I'll just need to go and remove the device from my test application earlier today. How do I do that? I'll just delete the device. I deleted the wrong one. Okay, we'll have to use the other one, the other example I created earlier. It doesn't matter. I've already shown you the procedure, so I'll go back over here and I will copy the app EUI from this app and the app key, and then we'll upload that again. So when this message stops appearing, we'll know that the device is connected to the network, which it has. And if we have a look now, we can see it was seen a few seconds ago. And we can see it's starting to send data through there. We can see it coming through in real time. So it should be once every 5 seconds. So you can see 55, 0, 5, so on. So the problem there was that I registered the same device to 2 applications. So you'll have to be careful about that. Okay, so now the device is connected to the LoRa network. Everything is fine, but at the moment it's not receiving any downlink messages, so it can't perform the OTA procedure. So to send a downlink message, you have to connect to the MQTT broker that the TTN network provides. So using some of these details that we noted down earlier, we can begin to fill out a command. They have a website for this already. If I go back to my slides, you'll be able to see they have a there's a guide by TTN that you can follow. That's where I got all of this from. So it's just TTN docs applications, then you click MQTT and quick start, and that will tell you how to go through all of that. So first we need to put our region in. So for me that's EU, but that might be slightly different for you. So we'll put EU in both of these. You then need to put your app ID, which will be the unique name you gave the app. So some of this has changed now because I'm using a different app than the one from earlier. So let me just have a quick look. What do I need? The app ID. So that will be the bit at the top here. So we'll paste that in. And then we'll need the device ID. So if you go to your devices, or if you've noted it down earlier, you can use that. So I just called it lowpi_1. So this is the uplink the topic. So we're connecting to this server with this topic, so it's the name of your app, your devices, the name of your device up, so that will show us all the data. And now we need to give it the login credentials, which will be the app ID, which if we go on the device, you'll get the application. No, sorry, that's the application ID. So that's the name of the actual application. So here it's Pycom _seb_OTA test. So we can put that in. And then the app key, that you need to go specific to the device. So we'll go through to the devices page and then we'll copy the app key from there. We can paste that in. That doesn't look correct. That's not the correct thing. It's this one here. It's the access key that you need at the bottom. So if you go to your application, you scroll down to the bottom and it says access keys. We'll want that. And that should be quite a long number, something like that. That looks correct. So this command here should subscribe us to the, we'll open a new window, type that in, and that should connect us to the MQTT broker, and here we can see the live data coming in from the device. So that's worked. And then Mosquito sub. So if you haven't before, you'll need to install Mosquito, which is an MQTT client for macOS. It's available for Linux and Windows as well. So the pub will, the Mosquito_pub command will let us send data to the MQTT broker. So we send it to the topic, the name of your app, devices, the name of your device, and then down. So this will be a downlink message for this device. And then here at the end, I'm just sending it a raw payload, and this is a base 64 encoded value that equals the command we set here in our code earlier. So if I copy this command, sorry, we can go over and we'll open a new window, and we can send that. And then if we go back over to our devices, and then data, and then if we filter out all the uplink messages, you'll see there was a downlink and it's been received by the device. So if we have a look here on the device is now performing the OTA. So if we go back over to the server, we can see that it's starting to fetch the data. So it might take a few seconds. Need to make sure it's connected to the correct Wi-Fi network. I've had to connect to a different network here to get the live streaming working, so if you just bear with me 2 seconds. No, that is my IP address, that's correct. We can see, yes, there we go, the update has started coming through now. It's requested the manifest, which has told it that it needs to get these different files, so it's now requesting those. And it's going to start writing them to the device. And what you'll find is it will go from a green LED to a blue one in just a moment when the update decides to work. It's not normally this slow. The demo gods have, of course, cursed me because I'm doing a live demo. Let's reboot and try again. So we'll just make sure everything's fine. We will clear the device just to make sure all the files are correctly uploaded when we upload them again. So here I have version, you can see at the top here I have version 1 open. The only difference between version 1 and version 2 in the Git repo is the color of the LED. One's green and one's blue. So we'll let that upload again. Should join the network. Okay, so if we go back here, we can see again the device is connected and it started sending messages to TTN. We'll go back over to our terminal. That one, and then we can send our downlink message again, and you can see that it's been scheduled and then sent there. So we can see the device again performing OTA, so it's started to connect. And then hopefully in just a second it will connect to the Wi-Fi and we'll be able to see it here. There we go. So it's, there we go, it's beginning to work this time. So now the device is rebooted. What I forgot to do is, remember how I said earlier you need to include the OTA code in both versions. I've made a mistake where I've not copied over the settings from the first version to the second one, and I've now broken it. So what we have to do is we have to copy over the TTN details that we just entered, and we need to put them onto the second version as well as the first version, otherwise it won't work. So let's give that another shot. So again, we'll do import os.mkfs flash. What this does is it just completely wipes your device to make sure that there's no leftover files, and we'll give this another shot. So you have to be very careful when performing OTA updates. You have to make sure that you test them thoroughly in the lab to make sure that you don't suddenly start bricking all your devices, because had I have done that in the wild, that device would no longer be able to receive updates because it wouldn't be able to connect to the LoRa network. So it's quite important that before you publish an update to lots of devices, you go through and make sure it does work. So we've joined the LoRa network. We'll push another downlink message. And then any second now we should see a message pop up here performing OTA. So at the moment you'll see that it's a green LED, and once the OTA is completed it should turn blue. There we go, you can see here the server is serving files to the device. The device is rebooted, and there we go, the LED has turned blue. So what had happened was our device was on version 1.00, and then our server had generated a difference of what it needed to go from one version to the next. So you'll notice it only downloaded OTA and main. It didn't download some of the other files, such as config, which contained the Wi-Fi settings, which I obviously can't show live on air. So I didn't bother pushing that file because it hadn't changed, and nor had getID. So it only updates the files that need to update, and as you saw, the device changed color, which is the difference in their main.py. So there we go. That is how we that's the demonstration of how you guys could implement firmware over the air. Obviously, this process could be a little bit more robust. This is something we're giving to the community as a sort of a basis, so that you can get an understanding of how the procedure should work, and how you can begin to do this on your devices. You could change it to be from Wi-Fi to work over Bluetooth maybe, or maybe you'd like to rather than using HTTP, you'd prefer to use FTP. You should still be able to use our OTA library and still be able to hopefully reuse some of this code in your own examples. I hope that helped everybody. I'll be around for a few minutes to take questions if you've got any, but if not, then thanks for watching. Okay, I guess it looks like there are no questions. If you do have any questions though, you can always either email support@pycom.io, or you can catch us on the forums. We'll answer any questions you've got. So thanks guys for tuning in, and we'll see you next time.